Hey everyone, back to a new awesome video, and today we're going to continue with our series about electricity and magnetism. Today we will continue exploring the applications of Gauss Law, specifically planar symmetry. First, we will understand what happens when we combine two infinite seats. After that, we will give those seats some width and they will become infinite slabs, and we will also analyze them. And finally, we will understand what happens when the charge density of the slab is not uniform. So, let's start! Alright, now let's try to understand what happens when we have two thin seats. We can see there's three different regions we're going to be interested in. We're going to have region 1 up here, region 2 in between the two seats, and region 3. We expect this situation to be kind of symmetrical, in a sense that these two parts should be similar to each other. We can see that this problem is equal to the addition of the electric fields of each of the thin seats. So what we are going to have in a smaller scale is this thin seat that is going to create an electric field in that direction, an electric field in this direction, an electric field in this direction, and over here we will have the negative one, and we need to add to this the contribution from the negative one, which we're going to have over here. This is the remnant of the other one, and we're going to have what we find, and what our intuition tells us, is that if these two superficial charge densities are the same, this electric field is going to be equal to sigma over 2 epsilon naught for each of the thin seats. Therefore, they are going to be equal but opposite in direction. Therefore, this one is going to cancel with that one, and this one is going to cancel with that one, and the ones in the middle are going to add up. Knowing that, we're able to apply Gauss law and find what the actual intensity for things will be. If we draw our Gaussian surface over, let's start drawing it over here. We expect this is going to be a zero contribution. Also from these sides, the cylindrical side, we're going to have also a zero contribution, and the only contribution is going to come from that one, which is going to have our n hat vector and electric field. That's going to be the sum of both. We could somehow guess that it's going to be sigma over epsilon naught, but let's carry out the calculation. We know the flux, the electric flux, is going to be equal to E times n hat times the area. So it's E times pi r squared. And we're going to be containing over there sigma times pi r squared. Therefore, and over epsilon naught. So we see there's a pretty clear cancellation over here, and we find that the electric field is going to be equal to sigma over epsilon naught, and it's going to be pointing in the downwards direction, which is in this case minus j hat direction. If we carry out a similar analysis, we will find a coherent answer for a Gaussian surface enclosing over here. We will find it with a negative sign and a positive j hat vector, which is going to end up pointing downwards. And we also see that the electric field cancels over here. So in general, E1 is going to be equal to E3 for these two thin sheets, which is 0. And the electric field in region 2 is going to be equal to minus the superficial charge density over epsilon naught in the j hat direction. That is the electric field from two thin sheets. Great, let's start analyzing the situation for an infinite slab. At first sight, we can clearly see that there's 4 very different regions to consider. We have this first region, this second region, this third region, and this fourth region. Because to define our unit vectors over here, this is going to be I hat, not j hat, and this is going to be j hat. And we see we're going to have symmetries over here playing, and the situation in this side of the x equals 0 is going to be pretty similar to the situation on that side of x equals 0. Note that the x equals 0 is going to have an electric field of 0. And we're going to have an E2 pointing in this direction because there's more charge going for that direction than in that direction. We're going to have the E1 in this direction, then the E3 is going to point in that direction, and the E4 is going to point in this direction. Now we'll start our analysis with the outer regions as they are simpler, and it's pretty analogous to what we did last time. We defined our Gaussian surface over here, and we're going to say this has an area A, and both of them are a distance S from the middle point, so that it is symmetric. We can see that the electric flux is going to be equal to, by defining our unit vectors, n hat 1 and n hat 4. We see both of them add, not subtract the flux, and we have E1 times the area, and as it is the flux, it's not a vectorial quantity anymore, plus E4 times the area. And as it is a symmetric situation, we know that both of these are exactly the same as we are considering magnitude, so we have 2E times the area. And now let's consider the charge enclosed. We're going to have rho, that is the charge density, times the area of this cylinder, times d, because it's the distance we're considering over here. So we can cancel out the area, and we find that the electric field equals rho times the distance over 2 epsilon naught, because it's charge enclosed over epsilon naught. Now this is the magnitude of E1 and E4, but we would like to find the magnitude of these quantities on the inside. Note that it doesn't depend on S, as in the case of the infinite thin sheet. Our Gaussian surface now is going to be defined over here, and this distance is going to be x now. It doesn't seem like it's equal, but let's say it's symmetric. This is going to be A, and the same A over here, and once again our unit vectors n hat 2 and n hat 3. Now the electric flux is going to be pretty similar to what we found earlier. We are going to do the magnitudes of the electric field 2 and the electric field 3, and we find it's really 2 times the electric field times the area. That's a flux. Exact same situation as earlier. But now we're going to have a charge density that is going to be depend on that x. It's going to be rho times x in this case. See, it's times 2 because the total value of the cylinder it's 2x over epsilon naught times the area. Sorry about it. And we see we have some cancellations over here, and we find that the electric field is equal to rho over x times epsilon naught. Now let's write the total electric field. We see that E of x of this slab is going to be equal to, when x is bigger than d over 2, we're going to have this electric field in region 1. So it's going to be pointing in the I hat direction, rho over d2 epsilon naught. Now, when we have x less than d over 2 and bigger than minus d over 2, that is x from d over 2, x minus d over 2. In this situation, we're going to have, this is I hat, sorry, rho x over epsilon naught times I hat. And note that when x is positive, this is going to point in the positive direction as expected. And when x is negative, it's going to point in the negative direction, also as expected. Therefore, this is valid for all of these, for both regions. And then we're going to have, for our last region, region 4, minus, as pointing in the negative direction, rho d over 2 epsilon naught, for when minus d over 2 is bigger than x. And this is the electric field from an infinite uniform slab. Great. Now let's consider what happens when the density, when the charge density is not uniform, but it's a function of x. As before, we're going to have x equals 0 over here, and x equals d over 2, and x equals minus d over 2. And we're going to have that the charge density is function of x like this, which really is something like this. It grows up to d over 2, where it's not defined anymore, and same over here. Well, it's really 0 after d over 2 and minus d over 2. So in this case, we're going to take advantage from the fact that the electric field at x equals to 0 is 0. We're going to define our Gaussian surface to be over here with one side on the 0 region and the other one over here, and this is going to be x. Now, when we apply Gauss Law, we're going to have the flux to be equal to 0 times the electric field in this region, same as before, pointing in that direction, so it's E times A, the electric field times A, in the second region, equals charge enclosed, Q enclosed, over epsilon naught. But now that charge enclosed is going to be a little bit more difficult because it's not a uniform charge density. Therefore, this is going to be an integral from all over our Gaussian surface, all its volume B, of the charge density that depends on x times dB. And we're going to find this is really 1 over epsilon naught, the area, as it's independent. It doesn't, the charge density doesn't depend on these directions nor the orthogonal one. So it's going to be area times function from 0 to x of b times the absolute value of x. However, as this is all positive and we're defining x to be positive, in this case we're going to see that this is really 1 over epsilon naught times the area b times x, and that is b x squared over 2. So we find our electric field to be in the second region. The a's cancel and we have bx squared over 2 epsilon naught. Now, if we want to consider the electric field in that region, what we are going to have, it's very similar analysis. Now this is I hat in this direction. The flux in that case is going to be the exact same. So A is going to equal this integral over here, and we can already stick out the area. And now we're going to have the integral from, let's draw the Gaussian surface so that you see it. It's going to be the integral from minus x to 0. So it's going to be integral from minus x to 0 of b absolute value of x dx. Now, what we see here is that all the values are negative, and therefore this absolute value is going to add a negative sign to it. So it's going to be equal to a b, let's take it out of the integral for simplicity, and the integral from minus x to 0 of minus x dx. Now, quick integration gives us ab over epsilon naught, that is minus x squared over 2 x prime dx prime, so that we can differentiate between this dummy variable and the actual x we have, from minus x to 0. Substituting 0 gives nothing, and minus this substituting the x squared gives us a b x squared over 2 epsilon naught. And now we can cancel some of these things. This is 3, sorry about that mistake. And we have that the electric field in this region is b x squared over 2 epsilon naught. And now it's when we apply the fact that that n hat vector was pointing on the other direction, and therefore this is minus and this is I hat. We are not going to consider the outer regions because it's really the same thing. We just have to integrate, but the final answer is not going to depend on x, is going to be a function of d over 2. So if we substitute d over 2 in this function, we will just find the answer for region 1 and region 4. That is all for today. I hope that you completely understood how to use planar symmetry to your advantage. In the next video, we will introduce cylindrical symmetry, and we will learn how to use it with some more examples that should give you more insight about Gauss Law. Any doubts left, you may ask them in the comment section, and I'll try to answer them in the best way I can. Remember to like the video if it was the case, press the subscribe button, the bell, and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!